April 2025. A subtle dip in the light of a faint red star reveals something unusual in the data. Astronomers report a potential biosignature from a world more than 100 light-years away, a spectral fingerprint of dimethyl sulfide in the atmosphere of the exoplanet K2-18b. On Earth, DMS is a gas produced almost exclusively by forms of life, and if this detection is confirmed, it would be the strongest hint yet of biological activity beyond our solar system. The news made headlines around the globe. Has the James Webb Space Telescope detected the chemical scent of life on a distant planet? In the silence of space, a new chapter unfolds in the search for life. But before drawing conclusions, we must understand the stage on which this drama is unfolding, the planet K2-18b itself. What kind of world could harbor such an enticing signal? Our journey begins with the discovery and nature of this intriguing exoplanet. K2-18b is a distant exoplanet orbiting the cool red dwarf star K2-18, located about 124 light-years from Earth in the constellation of Leo. This alien world was first discovered in 2015 by NASA's Kepler Space Telescope during its K2 mission, when astronomers noticed the planet periodically transiting its star, causing tiny dips in starlight. From those dips, they deduced the planet's basic properties. Its radius is about 2.6 times that of Earth, and its mass around 8.6 Earth masses. And that places it in the category of a sub-Neptune or mini-Neptune, larger than Earth, but smaller than the ice giants Uranus and Neptune. Despite its size, the planet orbits within the habitable zone of its star, a region where temperatures may allow liquid water to exist. A year on K2-18b only lasts about 33 days, which is rather short. But thanks to its close orbit around a dim star, the planet receives roughly the same amount of light from its red sun as Earth does from ours. Its estimated average temperature is about 265 Kelvin or 17 degrees Fahrenheit, potentially Earth-like, depending on the greenhouse effect. It's worth noting that K2-18b stood out early on due to its location and composition. In 2019, using the Hubble Space Telescope, scientists detected water vapor in the planet's atmosphere. It was the first time water vapor had been seen on a small exoplanet in the habitable zone, a discovery that stirred excitement worldwide. It confirmed that it meant the planet could have a substantial atmosphere containing water, a key ingredient for life. This discovery placed K2-18b on the map as a prime target for further observations. Could it be an enlarged version of Earth, or something more exotic? Soon, all evidence pointed to an entirely new class of planets. So, K2-18b doesn't quite fit into the usual categories of rocky Earth-like planets or gas giants. Instead, scientists suspect it may belong to a recently proposed class of exoplanets known as Hishian Planets. The term Hishian is a portmanteau of hydrogen and ocean. Coined in 2021 by a team at Cambridge University to describe planets covered in oceans and shrouded in hydrogen-rich atmospheres. These worlds are larger and with a higher mass than Earth, potentially around 2.6 times Earth's radius and up to 10 times its mass. Yet it could still offer temperate surface conditions. K2-18b fits this profile almost perfectly. It's been dubbed the leading Hishian candidate. What might a Hishian planet be like? The concept describes a world with an ocean hundreds of miles deep, covered by an atmosphere dominated by hydrogen and possibly helium. An atmosphere like that is much lighter and less dense than Earth's nitrogen-oxygen blend, allowing it to extend farther into space. A thick hydrogen blanket could act as an insulating layer, possibly helping retain oceanic heat. Hishian planets could orbit mini-stars. Astronomers believe sub-Neptunes of this size are extremely common in our galaxy. Yet for a long time, these mid-sized planets were not a focus of study. That is now changing. The potential of such planets is prompting astronomers to rethink the boundaries of habitability. According to Nico Madhusudan, an astronomer at the University of Cambridge and lead author of the paper announcing the discovery, such findings underscore the importance of considering diverse, habitable environments. Traditionally, the search for life on exoplanets has focused on smaller, rocky planets, but the larger Hishian worlds are significantly more conducive to atmospheric observations. In other words, although these planets may resemble mini Neptunes more than Earth, they might offer the best chances for detecting signs of life, since their dense atmospheres are easier to probe across light years. The idea of Hishian planets has opened new possibilities for our imagination, but to truly understand the nature of K2-18b, we must study its structure and atmosphere as closely as the data allows. We can infer the internal structure of this planet from its size and density. With a density of about 0.1 pounds per cubic inch, K2-18b is neither purely rocky nor a gas giant. The best models suggest this is a layered world. At its center, there's likely a rocky core made of silicates and metals. Above it, pressure forces water into exotic forms, a mantle of high-pressure ice. And above this solid mantle, there could be a vast ocean of liquid water if the conditions are right. All of this is surrounded by a dense atmosphere rich in hydrogen and possibly helium. Essentially, K2-18b may be an ocean world with no land, a planet of global seas under a thick hydrogen-dominated sky. Whether or not a liquid ocean exists on this planet depends on the thickness of the hydrogen atmosphere. If the atmosphere is too thick, the water beneath it would be subjected to crushing pressure and heat, possibly forming a supercritical fluid, not a true liquid or gas, but an environment likely hostile to life. On the other hand, if the hydrogen layer is relatively modest, the water layer could maintain conditions more similar to Earth's, favorable to life. The issue was discussed during early research stages. Initial estimates suggested that water on K2-18b could exist in a hot, supercritical state without a distinct ocean surface. However, later analysis, especially using new JWST data, indicated that the atmosphere might not be too dense. There are signs pointing to a real ocean-atmosphere interface. In other words, an actual liquid water ocean beneath the gas. One of those signs is the absence of ammonia. Presence of ammonia is expected in a hydrogen-rich atmosphere unless it has somewhere to go. A liquid ocean would be the perfect sink for it since ammonia dissolves easily in water. JWST detected methane and CO2 in the air on K2-18b, but little ammonia, which supports the hypothesis that a water ocean may exist beneath the hydrogen-rich atmosphere. If the ocean does exist, it may be very deep, much deeper than any on Earth, and possibly warm, depending on heating from the planet's interior and atmosphere. The ocean may be hidden under thick clouds where moist hydrogen-rich air meets the cooler layers of space. As we mentioned earlier, beneath this ocean, pressure would eventually cause the water to freeze into ice, potentially preventing direct contact between the water and the rocky core. This has implications for life. Without mineral circulation at the ocean floor due to the ice layer, nutrients could be limited, potentially posing a challenge for any biological activity. Still, life in such a world might resemble Earth's deep-sea extremophiles, drawing energy from chemical gradients or faint filtered starlight from above. However, these ideas remain a speculation for now. What we do know comes primarily from one source, the James Webb Space Telescope, which was able to sniff the air of K2-18b and determine its composition. And that's where we'll focus next. To uncover the atmospheric secrets of this distant world, scientists turn to JWST, which excels at infrared spectroscopy, detecting these molecular fingerprints in faraway atmospheres. In 2023, JWST observed K2-18b as it passed in front of its star using the near-infrared imager and slitless spectrograph and the near-infrared spectrograph. Here's how it works. Every time K2-18b transits its star, once every 32.9 days, a tiny fraction of starlight filters through the planet's atmosphere. Molecules in that atmosphere absorb specific wavelengths of light, leaving dark lines or features in the spectrum. By splitting the starlight into a rainbow and analyzing the missing parts, Webb can identify the chemical ingredients of the air. It's like reading the planet's chemical barcode. This transit spectroscopy method used by Hubble to first hint at water vapor on K2-18b is now employed by JWST, which has far higher sensitivity and a broader range of wavelengths. The observations from this space telescope did not disappoint. In the infrared spectrum of the atmosphere, clear signs of carbon-bearing molecules were found. Specifically, James Webb definitively detected methane and carbon dioxide in the air. These findings, announced at the end of 2023, mark the first solid evidence of atmospheric composition on a sub-Neptune located in the habitable zone. Several wavelength ranges contain methane, others contain CO2, indicating a hydrogen-rich atmosphere containing these gases. Water vapor is also expected to be present, although spectral details suggest that if it exists, it is in small quantities in the upper atmosphere, or possibly in the form of high-altitude clouds. Notably, as mentioned earlier, ammonia was largely absent, which combined with methane and CO2 strengthens the case K2-18b may indeed be a Hishian world with an ocean beneath. Scientists have created a transmission spectrum chart of the planet's atmosphere showing how much starlight is absorbed at different wavelengths. The blue line represents the model that best fits the JWST data. Prominent absorption features indicate the presence of methane. The areas marked in purple, red, and green highlight the signatures of these molecules, with an intriguing segment around 3.3 microns hinting at the presence of dimethyl sulfide, or DMS. What does this mean? Let's break it down. So, within this spectrum, scientists noticed a particular feature, an absorption spike that didn't match any molecule expected to appear in standard sub-Neptune atmospheres, except for one. When they ran atmospheric models, the data showed a tentative match with the presence of dimethyl sulfide gas at certain wavelengths. The team reported this as a possible detection of DMS, though with a low degree of confidence. We'll discuss the caveats shortly. Still, it was enough to spark increased interest because on Earth, DMS is closely linked to life's processes. Thus, JWST's data covering wavelengths from roughly 1 to 5 microns painted a picture of K2-18b as a hydrogen-rich world containing methane, CO2, and possibly even a molecule that on our planet is associated with life. This was a milestone moment. The first time a combination like this was detected on a planet in the habitable zone of a star. So here's what we have. JWST detected an atmosphere that could match a potentially habitable ocean-bearing planet. Methane and carbon dioxide are abundant, ammonia is scarce, and unexpectedly, there's a hint of dimethyl sulfide. These indicators suggest that the atmosphere may be in contact with an ocean and perhaps influenced by biological activity. But how convincing is this version of the story? The next step is to understand why DMS is so significant and why scientists are approaching this result with caution. So, the reason dimethyl sulfide caused such a stir is what it represents here on Earth. It's known that on our planet, DMS is almost entirely produced by life. It's a sharp, sulfur-containing gas often associated with the smell of the sea, a faint aroma of cabbage, or an ocean breeze noticeable near blooming plankton. In Earth's oceans, microscopic marine plankton, particularly some species of phytoplankton and bacteria, synthesize a compound called DMSP, which they use to regulate their cells. When these organisms die or consume food, DMSP breaks down and releases the gas DMS. As a result, most of the DMS in Earth's atmosphere comes from marine phytoplankton. There are virtually no significant abiotic non-biological sources emitting this gas into the air in large quantities. Volcanoes and hydrothermal vents, for example, emit various sulfur compounds, but not much dimethyl sulfide. Therefore, on Earth, if you detect DMS, you're essentially detecting signs of life. That's why DMS has been proposed as a potential biosignature gas for exoplanets. It's akin to stumbling upon a campfire smoke in a forest. You'd immediately suspect someone's there, because fires rarely start on their own. Moreover, this gas is short-lived in the atmosphere. On Earth, the molecule breaks down under sunlight, typically lasting between a few days and a few years. This means a continuous active source is needed to maintain a noticeable concentration of DMS. If K2-18b really does contain this compound in detectable amounts, it implies that something on the planet is regularly emitting the gas. For astrobiologists, that something could very well be biology, an alien biosphere in a hypothetical ocean. It's also important to note methane, also found on K2-18b, is often considered a biosignature in its own right when detected alongside CO2, in the absence of large amounts of carbon monoxide, because on Earth methane can be produced by microbes. In the case of an exoplanet, methane could also form abiotically, for instance through hydrothermal reactions or during the planet's initial formation. So it's not a smoking gun on its own. However, methane plus carbon dioxide together without ammonia is intriguing. Some researchers argue that this combination is hard to sustain without biological sources, because methane tends to break down via photochemistry unless there's a powerful replenishing source, which life can be. Add to that the tentative detection of DMS, and you get a potentially compelling argument that something biological could be at work. However, extraordinary claims require extraordinary evidence. At this stage, a hint of dimethyl sulfide is far from confirmed, and scientists are approaching it with a healthy dose of skepticism. Let's look at why caution is warranted and why alternative explanations and challenges must be considered. The hype surrounding the possible detection of DMS is tempered by the fact that the evidence is not yet conclusive. According to the researchers themselves, the signal from JWST data has low statistical significance, about 3 sigma, which means there's roughly a 0.3% chance that the signal is just noise. In scientific terms, 3 sigma is considered tentative, whereas the gold standard for discoveries is typically 5 sigma, which corresponds to about 0.00003% chance of coincidence. In an explanatory note accompanying the Nature news piece covering this finding, other astronomers pointed out that the team is really pushing the limit of what JWST can do with this detection. Exoplanet observation data is extremely complex. We're searching for tiny absorption features buried in the noise of a very faint signal, the light of a star passing through a thin ring of atmosphere around a distant planet. Instrumental noise, the choice of data processing methods, and stellar activity can imprint themselves on the signals in ways that either mimic real molecular signatures or obscure them. In fact, an independent reanalysis of the 2023 JWST dataset by another group found no significant signs of DMS or any other biosignature gases, suggesting the initial hint might have been a statistical artifact. These scientists describe the spectrum as rather noisy and warn that what one team sees as a spectral feature could just as well be random noise fluctuations. Another important point, the JWST data points to the presence of either DMS or a related molecule called dimethyl disulfide or DMDS. DMDS has a similar spectral fingerprint in some wavelength ranges and can form through chemical reactions in an atmosphere containing DMS. For example, dimethyl sulfide can oxidize or bond to form DMDS. Therefore, the detection may be some combination of these sulfur-containing compounds. If it's DMDS, the biological interpretation may shift slightly. This molecule can also be produced by life on Earth as some plants and microbes emit it, but it can also arise abiotically through photochemistry involving other sulfur species. Current data does not allow for a clear distinction. Perhaps most importantly, we must consider abiotic explanations for dimethyl sulfide, which could indeed exist on an exoplanet. Laboratory experiments and modeling have shown that certain chemical processes can generate DMS abiotically. For example, researchers have demonstrated that organic compounds exposed to high-energy radiations, conditions resembling a primitive atmosphere or cometary environment, can form small organosulfur molecules. Remarkably, in 2024, a team from the University of Bern, Switzerland, discovered DMS in the coma of a comet, K2-18b Churyumov-Gerasimenko, which the European Space Agency's Rosetta spacecraft had been chasing for 2 years, collecting direct samples from the dust and gas cloud released by the icy rock. Comets are lifeless, icy bodies, yet dimethyl sulfide was identified as part of their chemical emissions. This proves the compound is not exclusively biological. Furthermore, the complexity of stellar activity must be acknowledged. The host star of K2-18b is an active red dwarf prone to flares and spots. Stellar flares can create ultraviolet radiation that alters atmospheric chemistry, potentially quickly breaking down molecules like methane or DMS, or conversely generating false signals of other molecules. Star spots, cooler and dimmer regions on a star's surface, can cause anomalies in transit spectrometry. If the planet crosses over a spotted region of the star, the spectrum of starlight can change in a way completely unrelated to the planet's atmosphere, leading to false detections. Analysis of James Webb data tries to account for these effects, but it's not straightforward. Until we obtain more transit observations and ideally confirmations from entirely different instruments or telescopes, the result remains tentative. The next few years of research will determine whether this whisper becomes a clear signal of life or it fades away as an intriguing anomaly. In the meantime, understanding the star K2-18 itself, its flare frequency, spectrum, age, it's all critical for context, since the star significantly influences the planet's habitability and how we interpret data about it. For now, scientists are sifting through data and planning new observations to confirm the atmosphere's composition, while also looking ahead to the next generation of telescopes that will allow us to study this world and others like it in greater depth. In the coming decades, even more powerful observatories are planned which could turn this preliminary conclusion into concrete confirmation, or even discover entirely new biosignatures. In particular, scientists are developing missions like the LUVOIR and the HABEX, both of which are conceptual flagship space telescopes proposed by NASA for the period beyond 2035. These future telescopes will surpass even the JWST in capability. For example, LUVOIR envisions a telescope with a primary mirror up to 16 yards in diameter. For comparison, the James Webb currently has 7 yards. With such a vast light-collecting area and advanced instruments, LUVOIR will be able to directly image the exoplanets and obtain extremely detailed spectra. HABEX is similarly designed as a specialized planet-hunting observatory equipped with a star shade. That's a large occulting screen that will fly in formation tens of thousands of miles ahead of the telescope to block out starlight, and that would allow the faint glow of nearby planets to be seen. Both concepts share a common goal: to find and study Earth-sized, potentially habitable planets around the Sun-like and smaller stars, and to examine their atmospheres for signs of life. What could such telescopes do for K2-18b and similar worlds? First, they could perform more sensitive transit spectroscopy. With mirror many times larger that of JWST, a LUVOIR-type telescope could gather far more photons from each transit of an exoplanet, significantly improving the signal-to-noise ratio of the spectrum. If JWST brings us to the threshold of detection, LUVOIR could confidently confirm the presence of DMS, or rule it out with certainty. Furthermore, a mission could cover a broader range of wavelengths, extending into the ultraviolet and deeper into the infrared, which JWST cannot reach. This would allow detection of other potential biosignatures or atmospheric indicators. For example, LUVOIR could search for substances like ozone in the ultraviolet or detect organic haze or other compounds at shorter wavelengths. Importantly, future telescopes won't be limited to transits. They may be capable of direct imaging of some exoplanets. Currently, K2-18b orbits very close to a relatively dim star, which makes direct imaging challenging. Capturing its light separately from the stars may prove impossible, even with a 16-yard mirror. However, the direct observation of thermal emission might be possible. A large infrared telescope could detect the glow from the planet's day side as it passes behind its star, offering another way to measure atmospheric composition and even map temperatures. In addition to LUVOIR and HABEX, other missions will also contribute. ESA's Ariel mission, scheduled for launch in 2029, will study the atmospheres of hundreds of exoplanets, including candidates like K2-18b, though in shorter wavelengths and with lower sensitivity than the James Webb. Nevertheless, Ariel will be able to refine measurements of known gases on K2-18b and detect any fluctuations. Overall, the next generation of telescopes, both in space and on Earth, will provide sharper focus and broader vision. And importantly, these missions won't view K2-18b in isolation. They'll study a wide range of exoplanets in similar size and temperature. If, for instance, DMS is found on several Hishian-like planets, it would strengthen the idea that something universal, possibly biological, is happening. If the compound is detected only here and nowhere else, it could mean that K2-18b is unique, or it could mean that the initial finding was simply a fluke. In any case, this world has become a benchmark for future exoplanet science. This saga highlights a turning point in our search for extraterrestrial life. For decades, the prevailing mantra was to find the next Earth, a twin of our world with a similar size, orbit, and star type. K2-18b is not like Earth in the traditional sense. It's much larger, likely has no land, and orbits a very different kind of star. In doing so, it has broadened the range of worlds that astrobiologists consider promising. Essentially, this distant world's greatest contribution so far is expanding the range of questions we ask about life in the universe. It has shown that our search cannot be one-dimensional. We have to cast a wide net, from rocky planets around sun-like stars to mini Neptunes around red dwarfs, from biosignatures like oxygen and ozone to more exotic substances. Imagine a century or more from now an interstellar probe launched from Earth, equipped with an advanced artificial intelligence and instruments, embarking on a long journey to this distant world. As it nears the K2-18 system, the probe's cameras capture a blue orb lit up by the ruddy light of a dwarf star. Confirming the suspicions of our telescopes, it sees a planet wrapped in thick clouds with a vast ocean beneath them. Upon arrival, the probe may descend through the dense atmosphere, parachuting down through a sky painted peach by the red star's light filtering through a hydrogen haze. It passes through cloud layers, directly sampling their composition. Fierce winds, far stronger than Earth's, may batter the capsule, but eventually it reaches a vast alien ocean stretching to the horizon in every direction, dark and endless. Overhead, the local star grows dimly, a smoldering red ember half the size of our sun, casting a copper gleam across the wave crests. As the robotic explorer sinks into the water, it finds a microbe from this alien ocean, confirming that we are not alone. Yet such a mission is far beyond our current capabilities. The distance of 124 light-years is staggeringly vast with today's propulsion systems, and for now we remain distant observers, decoding faint spectra and refining our theories. Transit by transit, spectrum by spectrum, we're drawing closer to understanding this world. And until we can send a distant probe, our vigilant telescopes will continue to listen to its whisper that when life speaks, even from a faraway ocean world, we will hear it.